All right, welcome to worksheet number 4, continuity. This corresponds to section 1.8 on our textbook. In this worksheet, we'll study another property of a function. Before we studied the concept of limit, how the graph looks like when you have the limit existing and all this stuff. Here we'll talk about a concept of continuity, which includes the property of a limit as well. When the graph of function does not have any hole or jump, we can draw a graph without a lifting pen, right? So that's kind of like a concept of continuity in terms of just looking at the graph. This is the actual definition of continuity. Let f of x be defined on an interval that contains a number a. Again, a is x value, f of x is y value, right? F of x is called continuous at x is equal to a. It's called continuous at x is equal to a if limit of f of x as x approaches to a is equal to f of a. So on the left-hand side, we're talking about the limit. And on the right-hand side, we're talking about function value, where we just plug in a into a function, right? So if these two numbers happen to be equal to each other, then we'll say our function is continuous at that point. Otherwise, we're going to say f of x is said to have a discontinuity. So discontinuity. So f is discontinuous at that point, or f has discontinuity at that point. All right, I'm going to look at this part and like kind of talk about it in more detail. Let me just move it up here. So to be continuous at x is equal to a, three conditions must be met. So I'm just kind of re-explaining what this is in three more detailed way. So first, you know how we talked about the limit? The limit has to exist. So the limit of f of x as x approaches to a, it has to exist. And then b, f of a has to exist. So f of a has to exist. And then the third condition is the limit and the function value has to be equal to each other. So 1 has to be equal to 2, right? So those three conditions must be met to be able to say that f of x is continuous. So you can kind of say that, so this is like a reverse way. If I know that f of x is continuous at a particular point, then we know that limit exists, right? And then we already know that function exists and they are equal to each other, right? All right, let's look at example 1. Scroll down here. So example 1, consider the following function f of x. Is it continuous at each of the given point? If not, which of the three conditions is not satisfied? All right, let's look at part A at x is equal to -2. So x is -2 is right here. First, does the limit exist? What's the limit of f of x as x approaches to -2? So from the previous worksheet, I'm approaching to -2. The graph goes like here. The height of graph is approaching to 1. If I'm coming from the left, also the height of graph is approaching to 1. So the limit is equal to 1. So yeah, limit exists. Limit is equal to 1. So first condition is checked. Second condition, how about f of -2? So when I plug in f of -2, notice that this circle is open, is empty. This circle is filled in. So function value is right here, which is 3. So yeah, f of -2 exists, which is equal to 3. So first two conditions are satisfied. But are they equal to each other? No, because the limit is 1, and then function value is 3. So the third condition is not satisfied because 1 is not equal to 3. So the third condition fails. So not continuous at x is equal to -2. Just by looking at the graph, there is a little hole here. My graph goes like this, except there's a hole, or there's like a jump. My graph goes like this, it jumps to this point, and it comes back to this. So there is like either hole or there's a jump, right? So that's why it's not continuous at x is equal to -2. All right, let's look at part B. At x is -1. X is -1 is right here. Okay, at this point. So to check the continuity, first I have to check the limit. So limit of f of x as x approaches to -1. -1 is here. If I'm approaching from the right hand side, my graph is approaching to like 0.8. If I'm approaching from the left, my graph is approaching to 3. So the left limit and the right limit are not the same. So limit doesn't exist. Does not exist because left limit is not equal to the right limit, right? So the first condition fails, so in order to be continuous, I have to have all 3 conditions satisfied, except for this question, the first one is not satisfying, so you're done. So not continuous. Let's look at part C at x is equal to 1. 1 is right here. So x is equal to 1. I can check the limit, but f of 1, I mean, the graph goes on forever. There's no point at x is equal to 1. So limit is infinity because graph goes up. But f of 1 doesn't exist. So this one does not exist, right? So already not continuous. So far, it's not continuous here at -2, not continuous at here, -1, not continuous at 1. How about at 2? Right here. So hopefully it's continuous there. 2, maybe like mark it with the red. So let's check limit of f of x as x approaches to 2. Well, if I'm looking at the left limit, my graph is approaching to 1. Height is 1, right? If I'm approaching from the right-hand side, it is approaching also height 1. So limit is equal to 1. So that's good. F of 2 is equal to 1. So my graph just goes like this, right? So at x is equal to 2, this is my y value, which is just 1. Oh, those two numbers are equal to each other. So 1 is equal to 1. So yes, continuous. So this function is continuous at x is equal to 2. Let's move on to the next definition. This is where we're looking at continuity from only one side. So let's look at the first definition. A function is continuous from the right if the limit of f of x as x approaches a from the right-hand side. You see the little plus sign? Maybe I can zoom in a little bit. So the right limit is equal to f of a. So continuous continuity, it was just saying limit of f of x as x approaches a. But here, they add a little plus. So this is right continuous, means you only look at the right hand side limit. And same for the left. There's a little negative sign. So you're only looking at the limit from the left-hand side. All right, I'm going to skip example 2, and let's kind of go to, there are 2 example 2. Let's look at the second example 2. All right, the question says, find where f of x is equal to x over x plus 1 is continuous. Here, the hint is where is f of x not defined. Again, when we have 0 denominator, right? So when is x plus 1 0 when x is equal to -1? So for f of x, only place f of x is not defined is when x is -1. So this one doesn't exist, right? Not defined there. So that's where it's not continuous. I mean, it's not continuous at x is equal to -1. Other places, the limit exists. The function is going to be exactly the same as the limit as we saw from the previous worksheet. So only problem we had was when we had the 0 denominator. That's when x is equal to -1. So here, where is it continuous? Everywhere except x is equal to 1. So I guess I have to answer the question. It's continuous everywhere. So I can say -infinity to -1 union with -1 to infinity. So all x except x is equal to -1 is where f of x is continuous. Next, example 3 and example 4. I'll kind of get started on it, and then I'm going to have you guys finish it. Example 3, find a. Where's the a? This a here. Again, this is piecewise definition. My function is split into 2 different portions when x is less than or equal to 1 and x is bigger than 1. So find a so that f of x is continuous for all x. So when we have a piecewise function, one place that we possibly do not have a limit is when the function is split. So because when x is -1, I'm looking at this function, this equation. When x is bigger than 1, I'm looking at this expression. So This is for left limit, this is for right limit, so only possibility that we have the no limit is when these two numbers are the different, right? So if limit exists at x equal to 1, and that means left limit and the right limit are equal to each other, and then we have a function value equaling that, then I think we're good. It's continuous for all x. So we want f to have a limit at x is equal to 1. That means I want the left limit, x goes to 1 from the left, to be equal to the right limit. Because when the left limit is equal to the right limit, then the limit exists. So when we look at this one, left limit, I'm looking at this value, right? So 3x plus a. So 3, 1 plus a. And for the right limit, I'm looking at this expression. So x squared minus 2x, x approaching 1, so 1 squared minus 2a. So 1 squared minus 2 times 1. So that's 3 plus a is equal to 1 minus 2, which is negative 1. So that means 3 plus a, I want 3 plus a to be negative 1, so a has to be, what is it, negative 4. So a is negative 4. So if a is negative 4, then the left limit and the right limit are going to be the same, negative 1. And then function value is going to be also negative 1 when I plug in 1 here. 3 times 1 minus 4 will be negative 1. So limit is going to be equal to the function itself. That means it's continuous. All right, it's going to be similar for example 4. I'm going to have you try it by yourself. And once you're done with example 4, then we'll meet back at the next topic. All right, so when you're done with number 4, example 4, we have a different property of a continuous function. It's kind of similar to the limit. When we have a bunch of continuous function, you can add 2 continuous functions and it'll be also continuous at that particular point. You can divide f by g, f of x over g of x. It's going to be also continuous, provided that g of a is not equal to 0. Again, 0 denominator, right? So you can multiply, add, divide continuous functions, and you'll have also continuous function. You can compose continuous functions, and then it will be also continuous. So it's kind of convoluted here, but basically, if you have 2 continuous functions, you mix them together, it'll be also continuous. And also, all elementary functions are continuous where they are defined. So basically, pretty much all the functions we know, polynomials, rational functions, square root, exponent like x squared, e to the x power, trig functions, sine, cosine, tangent. So wherever they're defined, the functions are continuous. So all the functions we learned so far, basically, they're continuous on their domain. All right, let's look at example 5. Use continuity to find the limit of sine of x plus sine x. Okay, this is complicated. And there's a limit. X is approaching to pi. Because sine is continuous, x is continuous, sine is continuous, you add 2 functions is continuous. This is just a mixture of continuous functions, so we know it's continuous. That means basically we can plug in the numbers. To find the limit, basically you just have to plug it in. So that's like a nice thing about continuous functions. So one of the reasons we are dealing with this continuity is if I know a function is continuous, then to find the limit, I just have to plug in the number. So because sine of x plus sine x is continuous at x is equal to pi, right? Because this is where x is going to pi. It's continuous everywhere pretty much. So it's continuous at that particular point. We can just plug in. We can just plug in x is equal to pi to find the limit. Okay, so my answer is sine of pi plus sine pi. Sine pi is equal to 0, so this will be sine pi plus 0. Again, pi plus 0 is pi, so sine pi is 0 again, so my final answer is equal to 0. All right, the next, I think this is the last theorem in this section, intermediate value theorem. Intermediate means like in between two things, right? So if you have a continuous function, something has to happen in the middle somewhere. That's basically what it says. F of x is a continuous function on the closed interval a, b. So this is x value a, x value b. On the graph, a is here, on the b, and the b is here. Let n be any number between f of a and f of b. Again, f of a and f of b, these are f of x values, so they're y values. So f of a is right here, this is a, so f of a is this height. B is here, so f of b is this height. And they say n is some number between f of a and f of b, so n is like on this graph, somewhere here. It could be here somewhere, it could be here. So n can be any number in like in the y-axis somewhere. So okay, that's the setup. Then there exists a number, at least one number, c, in AB. So c's got to be between a and b, somewhere here. So c is the x value, right? So I'm going to maybe label this as x value, such that, so what is special about this c? F of c is equal to n. So whatever n value you chose, I can find the c such that f of c is that n, right? So this is called intermediate value theorem. This is possible when you have continuous function. If it's not continuous function, then we can't say for sure this is going to happen. But if it's continuous function, then any n you pick between f of a and f of b, I can find the c such that f of c is that value. That's what it says. Another way to look at it graphically is, let's say n is somewhere else, like n is here. So graphically, continuous function means my graph doesn't have a hole or it doesn't jump. I have to be able to draw from one point to the next point without lifting my pen. So choose n here. So let me kind of draw the line, extend the line here. If I were to draw a graph from f of a to f of b, n is between f of a and f of b, so it has to cross it somewhere. Like, it's not possible for me to go from f of a to f of b without lifting and not crossing n, right? So graphically speaking, if you have n anywhere between these two, if I were to draw the graph of it, how can I not cross it? I have to cross it if it's continuous. There's few ways I can cross it, but it cannot be continuous because I can go here, I can jump over and then go there, and then I don't have to cross n, right? So that's why it only works for continuous function. Let's look at the case where this theorem is not true. So if function is continuous, it has to be true. So right, so if f is not continuous, I'm going to draw a picture where the theorem is not true, continuous. So let's draw something like this. This is my a is 1. This f of a is here, right? And then draw like this. There's a little gap, like this. I just made it up. B is here. So f of b is over here, right? So I draw a function that is not continuous. So I go like this. There's a little jump. Then I go like this, right? So a is here, b is here, f of a is here, f of b is here. Now my n is any number between f of a and f of b. So I'm going to choose it to be 3. That's my n. So according to the way I draw the graph, can I find the c such that f of c is equal to 3, right? Here, like, can I find the graph such that the graph passes through, the y value of graph is 3? It never happens here. Here, y value is 5, y value is 4, y value is 1.9 or whatever, but y value is never equal to 3. So I cannot find c such that f of c is equal to 3. So not possible. And the reason this is not possible is because it was not a continuous function, right? So I just want to give you an example of that. Part 2 is a little bit too technical, so I'm just going to skip that. I'll just have to know part 1 would be a good example. Let's look at the application here. It says that if f of x is continuous and f of a and f of b have opposite sign, what does that mean? That means one is positive, one is negative. F must have a root in a and b. Root means f of x has a root, means f of some number is equal to 0. A root means where a function goes through 0, right? the y value of the function is equal to 0. So why is this true? It says f of a and f of b have opposite sign. That means one of them is positive, one of them is negative, and 0 is the number in between. So like our n has to be between f of a and f of b. So if one is positive, one is negative, then 0 definitely is in between those two. So for example, f of a is positive and f of b is negative, then n is equal to 0 is in between f of a and f of b. So that's exactly what the theorem says. If n is between f of a and f of b, then there is a number c such that f of c is equal to n. In this case, n happen to be 0. That's why we have a root. So for example, like a is here, let's say, so this is f of a, b is somewhere here, maybe my graph is like over here, so this is f of b. So f of a is positive, f of b is negative. Again, it's continuous function, so I have to cross at some point. So it crosses the x-axis, which means y is equal to 0. So this is n is equal to 0. So it happens right here. So this happens to be c then. That will help us to solve example 6. Show that x cubed minus 3x squared plus 1 is equal to 0 has a solution. So this is kind of basically saying a root, because root is where this thing becomes 0. So they could have said, show that x cubed minus 3x squared plus 1 has a root. This is exactly the same thing. Interval 0, 1. So okay. So this is going to be my a is going to be 0, b is going to be 1. So f of a is f of 0. Plug in 0, 0 cubed minus 3, 0 squared, so 0, 0, 1. F of b is equal to f of 1. Plug in 1, 1 cubed minus 3 times 1 squared plus 1. That's going to be 1 minus 3 plus 1, so negative 1. Okay. So here f of a is positive 1, which is positive. F of b is negative 1, which is negative. So I can kind of use the previous theorem here, application here. When they have an opposite sign, then it must have a root in between a and b. So according to the intermediate value theorem, so according to the IVT, I'm being lazy, intermediate value theorem, IVT, there is a c between 0 and 1, which is a and b, right? 0 and 1, a and b, such that f of c is equal to n, which is 0. Right? Because f of a is positive, f of b is negative, so I can say n here. I think I forgot to write that. Let n to be 0. Okay, because 0 is between positive number and a negative number. So okay, that's it. I think that's it for this worksheet.